Hello friends, good evening and welcome to our next chapter of slope deflection method. Next problem on slope deflection method. So we have seen different types of continuous beams wherein we have two or three spans together and different combination of loadings. So today we have only single span beam, and this single span is a unique span. If you see in the diagram here, there are two parts of the span. One span is having moment of inertia value 2I, another span is having single I value. It means there are two beams of different depths which are connected together at junction B, and at junction B we have two loadings. One is 40 kilonewton meter anti-clockwise couple and another is 10 kilonewton vertical load. So we have to analyze this little bit complicated beam using slope deflection method. So let us start with this. Okay. So our first step will be determining kinematic indeterminacy of this beam. So what will be that? Now this is a little bit tricky part. I am saying kinematic indeterminacy for this particular beam is 2, and those two unknown displacement quantities are, one is rotation of B and another is linear deformation or linear displacement of joint B. Now why there are two displacement quantities on this particular joint? There is a reason. This is a junction of two different beams having different depth. If you see, this is 2D and this is 1D. Okay, that is why moment of inertia here is 2I and 1I. So this particular joint is getting subjected to two displacement quantities. Rotation because of couple and linear displacement because of linear load. Okay, angular load, angular displacement, linear load, linear displacement. So in short, we are assuming that this is one imaginary support. In reality, this is not there. We are just assuming it. Okay, so this is how we are going to start with. And as compared to previous problems of continuous beams by slope deflection method, there will be less calculations involved. However, the unknowns and generalized equations will be much more there, and they will be more lengthy. So let us start again and proceed with the further analysis. So second step will be finding out fixed end moments. Okay. So what are these fixed end moments? Now please remember, it is only one span, but we have divided this particular beam in two spans. We are assuming this imaginary support here. So A to B is one span, imaginary, and B to C is another imaginary span. And if you see, A to B there is no loading, no intermediate loading, only joint B is subjected to these two loads. B to C, again there is no intermediate loading. So what we can say is, for this imaginary span AB as well as BC, fixed end moments are 0 because no external loading. Okay, so MF AB, it is equal to MF BA, it is equal to then MF BC, and then finally MF CB, it is equal to 0. Okay, so everything is 0. Third step will be slope deflection equations. Now these will be lengthy. We shall see why these are lengthy equations. Okay. Slope deflection equations. So MAB, what will be MAB? Let us first of all write our equation. 2EI by L into bracket 2 theta A plus theta B minus 3 delta by L minus MFAB. Okay. So here I value is 2I. So substitute 2E into 2I. Okay. 2E into 2I divided by span for AB is 8 meter. So it is 4EI by 8 multiplied by, do we have any rotation of joint A? No. Why? Because it is fixed joint. So theta A is 0. Theta B is unknown. So theta B minus 3 delta B upon 8. Do we have any value of MFAB? No. Nothing. So simplify this. So 4EI upon 8 into bracket theta B minus 3 delta B upon 8. Okay. So we have this first equation. Okay. Now come to second part. So what will be second part? MBA, second moment. Okay. MBA, not MFBA. So let us again write slope deflection equation for this one. So 2EI by L into bracket theta A plus 2 theta B minus 3 delta by L plus MFBA. Okay, this is our equation. So again 2E into 2I upon 8 into bracket again theta A is 0, fixed end 2 theta B minus 3 delta B upon 8. So MFBA is 0. MFBA 0. Okay. So again simplify this. So this is 4EI upon 8. So this is 4EI by 8 into bracket 2 theta B minus 3 delta B upon 8. Okay. Then the next pair of moments, MBC. What will be MBC? 2EI by L into bracket 2 theta B plus theta C minus 3 delta upon L minus MFBC. Okay. So 2EI, now here I value is 1I. For span BC, I value is 1I. So 2EI divided by 4. Remember L span of BC is 4 meter. So 2EI by 4 into bracket 2 theta B. Now this 3 delta by L term will be actually plus. Okay. So let us rewrite this plus 3 delta B upon 8. Why? Because if you compare A to B, position of B is down with respect to A. Okay. B is going down with respect to A because of delta. Okay, actually it is going down like this. But if you compare C, corresponding to B, C is up. So when it is upward, 3 delta by L is plus. Okay. So this is plus 3 delta B by 4, not 8. So MFBC is again 0. So this will be we will keep it as it is. Then MCB, it is equal to 2EI upon L into bracket theta B plus 2 theta C. Here we will write plus 3 delta upon L plus MFCB. So it is 2EI upon 4 into bracket theta B plus 3 delta B by 4. That's it. Okay. This we will proceed to step number 4. Step number 4 is equilibrium equations. So we know we have to combine these equations, slope deflection equations, and we have to form two simultaneous equations. Why two? Because we have two unknowns, correct? So we need two conditions of equilibrium or equations of equilibrium. So which are they? They are, one is related to moment, another is related to reaction. So let us go to our first equation of equilibrium, that will be MBA plus MBC, it is equal to minus 40. Okay, because this is anti-clockwise couple given in the loading diagram on junction of B, and on junction of B we have an imaginary support. It means there are two members meeting on joint B, one is BA, another is BC. So moments in these two members will be equal to external moment. Okay, so let us substitute MBA and MBC from the previous steps. Okay, so let us go. So what is MBA? 4EI by 8 into bracket 2 theta B minus 3 delta B upon 8. MBC, see here, 2EI by 4 into bracket 2 theta B plus 3 delta B upon 4. So this is MBA plus MBC. It is equal to minus 40. Let us simplify this. So take 4EI by 8 common. Okay, 4EI by 8. So 4EI by 8, if it is common, we have to multiply to this bracket by 2 and divide by 2, so that effect remains same. So from first bracket we have these two terms as it is, 2 theta B minus 3 delta B upon 8. Here we have to multiply by 2, divide by 2 for each term. Okay, so it will be 2 theta B as it is, because 2 into 2 divided by 2, again effectively it will be 2. Okay, so 2 theta B plus, here we have to multiply and divide by 2, so plus 6 delta B upon 8, it is equal to minus 40. Okay, simplify this ahead. So 4EI upon 8 into bracket 2 theta B plus 2 theta B is 4 theta B, then plus 6 by 8 minus 3 by 8. So it will be effectively plus 3 by 8. So plus 3 delta B upon 8. It is equal to minus 40. Again simplify this. Bring this 4EI by 8 on right hand side. So 4 theta B plus 3 delta B upon 8. It is equal to, so 4 by 8 is 1 by 2. 1 by 2. So effectively 2 goes to the right hand side. So it is minus 80 upon EI. Okay. So what will be then theta B? So it is minus 80 upon EI minus 3 delta B upon 8 into bracket 1 by 4. Outside the bracket it will be 1 by 4. So what is theta B? Minus 80 by 4 is minus 20 upon EI, and minus 3 by 8 into 1 by 4 is minus 3 by 32. So minus 3 delta B upon 32. Okay, this is equation 1. This will be our first equation. We will frame one more equation from another condition of equilibrium. What will be that condition of equilibrium? Let us see. So we have now external force which is vertical in our loading diagram. So what we are going to do is, we are going to take the help of that particular external load. So if you see, I am going to separate out both parts of the beam. One is with 2I moment of inertia, another is with 1I. Okay. So here we have 10 kilonewton load, and I am going to assume the moments on these ends. This is A, this is B, this is C. Okay. So I am going to assume now the clockwise moments on both the ends of AB span as well as BC span. I can assume these two moments as anti-clockwise also, one clockwise, another anti-clockwise also. So I have freedom to select the direction of these moments. Okay, so this will be MBA actually, this is MBC, and this is MCB. Okay, now please see, on both the ends for both the parts I have assumed clockwise moments. Okay, MAB, MBA, clockwise moment. So if we want part AB to be in equilibrium, reactions on A and B should be such that these reactions are causing opposite sense of movement. So if it is subjected to clockwise moment, reactions should be such that anti-clockwise moment is created by reactions. So we have this reaction RAB or RA. Let us say this is RAB just for reference, and this is RBA. Okay, this is RBA. So similar set of reactions will be there on BC. So this is RBC and this is RCB. Okay. Now we have to relate RBA and RBC to 10. So what will be that? Internal reactions RBA minus RBC, it is equal to minus 10. Okay, it is equal to minus 10. So this is our second condition of equilibrium. Now we will substitute RBA and RBC in terms of moments and span, and then again we shall simplify and we shall see such another equation. Okay, and then we shall solve simultaneously. So here we are going to now substitute reactions from these two free body diagrams, and I have simplified this up to equation number 2. I'll just explain you because it will be very much time consuming. Okay, so I have written RBA as MAB plus MBA upon 8. I have taken this RBA as this particular value from this free body diagram. I have taken summation of moment about A, it is equal to 0, and I'll get RBA as MAB plus MBA upon 8. Similarly, RBC also I have taken as this particular bracket from free body diagram of span BC. So it is MBC plus MCB divided by 4. I have got minus 10 on left hand side, it has become plus 10. Now we are going to simplify this step by step. So MAB, refer to our previous steps. Step number 3. Step number 3. In this step, you will get all these MAB, MBA, MBC, MCB values. Okay. Substitute these values from step number 3. So MAB, I have substituted this as 4EI by 8 into bracket theta B minus 3 delta by 8. Then MBA, this particular value, plus 10. Okay, it is here plus 10, minus MBC, this value, MCB, this value, divided by 4. Okay, so this is equal to 0. Now I am going to simplify this ahead. So I have taken 4EI upon 8 into this 8 in the denominator. Please see. Okay, 4EI upon 8 into 8. So this is 4EI upon 8 into 8 into bracket. This is theta B plus 2 theta B. So this becomes 3 theta B. Then minus 3 delta B by 8. It is 2 times. So this becomes minus 6 delta B by 8. Okay. So the simplification of this particular first term is this small one. Then plus 10. Then third term, it is here. 2EI upon 4 into 4. Okay. So 2EI upon 4 into 4 into bracket. 2 theta B plus 1 theta B is 3 theta B. Then 3 delta B by 4, 3 delta B by 4, 2 times. So 6 delta B by 4. So it is equal to 0. Next, what I have done is, I have taken EI by 16 common. Okay, so this is 4 EI upon 64. So 4 by 64 is 1 by 16. So this is EI by 16. Here, it is 2 EI upon 8. So I want here to multiply and divide by 4. Okay, not 4, 2. I will have to divide this to the bracket by 2. Okay, so this becomes 3 theta B. This is minus 6 delta B by 8. This becomes minus 6 theta B. This becomes minus 24 delta B by 8. Okay, and plus 10 is here. It is equal to 0. So 24 and 6. Let us go step by step. EI by 16. So what has become theta B and minus 6 theta B? Minus 3 theta B. Then minus 6 delta B by 8 and minus 24 delta B by 8. It becomes minus 30 upon 8. So minus 30 upon 8 is nothing but minus 15 by 4 delta B. And plus 10 is equal to 0. So here 3 theta B plus 15 delta B by 4, it is equal to 160 upon EI. So we are going to just substitute back value of theta B from equation 1 to equation 2, and then we shall simplify. Okay, so let us start ahead and proceed with the next part of the analysis. So here I have again simplified for the next steps. So I just explain them. We have come up to step number 2. Now in step number 2, we are going to take value of theta B from equation number 1. So equation number 1 is here, that we can see here. This as it is we have substituted here. Okay, so 3 times minus 3 delta B by 32 minus 20 by EI. So this is 3 theta B plus 15 delta B by 4. It is equal to 160 upon EI. Now we are going to simplify this for delta B. It means we are going to find value of delta B from this. So simplified here is like this. I'm just coming here. So 3 into 3. So minus 9 delta B by 32. 3 into 20 is 60 upon EI. Then 15 delta B by 4. It is equal to 160 upon EI. Okay. So we have expanded this bracket. Now we are going to take some of the things common. So delta B we have taken common from first and third term, and we have made the denominator equal. So it is 32. So this is 4 into 8. Okay, it is equal to 32. So it has to be 15 into 8, 120. Minus 9 will be as it is because this is 32. Okay, so minus 9 plus 120 is 111. Okay, so delta B will be finally 7040 upon 111 EI. So this value will be substituted back to equation 1. Value of delta B will be substituted back to equation 1. We will get theta B. So theta B comes to be minus 2880 upon 111 EI. Now we have got both our unknowns, theta B as well as delta B. So we will again keep these values in step number 3 and we will get final moments. Now we will see what are the final moment values. I have taken these equations from step number 3, slope deflection equations. I have substituted in that step values of theta B as well as delta B along with their signs, and we can see that MAB is minus 24.86 kilonewton meter, then MBA minus 37.4 kilonewton meter, MBC minus 2.16 kilonewton meter, MCB is plus 10.81. So we just have to cross check that the algebraic addition of MBA and MBC is minus 40. Okay, so minus 37.4 and minus 2.16, it is minus 40. Okay, so let us plot now the ordinates of moments and draw BMD. We need not draw here shear force diagram. Why? Because there is no point of zero shear force anywhere. So MAB is minus 24.86. So we shall plot it here. Minus 24.86. Okay. Then go to BA. So it is 37.4. Okay, with minus sign. Then it is minus 2.16. So it will go up 2.16. Then last is 10.81. So it is somewhere here. 10.81 kilonewton meter. Okay. So this will be your BMD. So this is minus and this is plus. Bending moment diagram on tension side. So compared to all the previous questions by slope deflection method, this particular single span beam is a little bit complicated, and as I told you, equations are very lengthy. However, if you keep your patience and continue solving, then you will get the correct answer. So friends, this was my analysis on this particular beam by slope deflection method. If you had any difficulties, do ask me and do write in the comment section. If you are new to this channel, subscribe the channel and hit the bell icon. Thank you very much.